Hello everyone, I'm Liana from Florida International University. Today I will be presenting our work titled Unifying the Data Center Caching Layer. I will consider if such unification is feasible and if so, would it be profitable? Computer data center nowadays consume storage using different storage types or interfaces, such as block, file, object, and key value. To accelerate performance, cloud data centers often deploy different types of caches. Such caches typically target a specific storage type, store instance, or simply workloads running on a single host or VM. On the right side, we see a typical software ecosystem for cloud computing, where we have applications and libraries that access different storage systems using different interfaces and are accelerated by distributed caching solutions. At the same time, new technologies such as 3D cross-point memories and NVMe SSDs are also becoming increasingly available. Each of these devices impose new requirements when used for caching. On the network side, high-performance network fabrics such as 40 gigabit Ethernet, Rocky, and InfiniBand are making data access over the network more efficient. In the rest of this presentation, we'll motivate our work, provide an overview of the proposed caching as a service solution. I will then present some results for a preliminary study to evaluate the advantages of our design. And finally, I will briefly discuss future work directions. Cloud data centers today run multiple applications using different storage system types. Applications running on each system typically have access only to the cache resources assigned to that host. As a result, cache resources get fragmented across different storage systems and also potentially across different nodes in the data center. Since these resources are expensive, a new solution that allows sharing all the available cache resources in the data center across storage systems and applications is desirable. Second, a majority of storage caching solutions implement write-through or write-down caching policies, thereby having no cache performance gains for write operations. However, write-dominant workloads in the cloud are commonplace. Among the collection of workloads analyzed in this paper, we find that block and object stores have 71 and 40.5% of writes, while key value and file have 22.5 and 9.8% respectively. Therefore, a storage caching layer that is unable to cache writes is likely to be limited in its effectiveness. Lastly, the diversity on caching devices that are getting deployed in the data center requires implementing optimizations for a specific cache device characteristics. This further motivates creating new caching algorithms once within a unified caching service instead of repeating these optimizations for multiple siloed solutions. To estimate the penalty of serving writes from the storage backend instead of the cache, we created a simple model where an application accesses a local and remote cache with block storage over the network. When the storage backend latency is 1 millisecond, the amount of throughput that is available for the application increases by 10 and 7 times respectively for local and remote caches, when the cache hit rate increases from 90 to 99%. Similar improvements are seen for larger storage latencies. Therefore, large performance improvements of using relatively higher performing local and remote caches sustain regardless of the backend storage latency. Next, we evaluate the performance benefits available when using higher capacity remote cache in comparison to a limited capacity local cache. When compared to a 10 GB local cache, increasing the size of the remote cache allows throughput increase of 1.24 times when increasing the cache size to 20 GB. And 18.7 when increasing the cache size to 100 GB, both at a queue depth of 8 IOs. This demonstrates that despite the added overhead of network access, there are significant performance gains to be had with larger capacity remote caches. To address these challenges, we propose in this work caching as a service, CaaS, a general distributed caching layer that abstracts and exposes all the available cache resources in the cloud for all types of storage systems. Typically, workload generators, including VMs, containers, and applications, access data residing in the backend storage over the network. Our proposed CaaS solution adds a CaaS client that interposes between the applications and the storage backend. This layer translates storage-specific requests into CaaS type requests using the translation layer. Cache clients communicate with cache data servers to access data. These data servers and the access to the cache service itself is managed by the cache coordination service that is implemented using a zookeeper cluster. The cache coordination service manages metadata and controls cache allocation, load balancing, and fault tolerance across cache data servers. Cache misses and asynchronous write-back calls are implemented by communicating with the storage backend through the cache client. Cache client and cache data servers can run on different hosts, in which case all cache data access incur a network hop, but they can also be implemented as containerized services running on the same host. The cache API is designed around the concepts of store and CLIs. Store is the unit of access protected cache provisioning, and CLIs is the unit of cache data access. Cache clients initially register with the coordination service, which provides cache allocation and a map of CLIs and CLIs locations for data being accessed from the storage backend if available. This map gets updated by the coordination service as data items get accessed and the cache gets populated. Cache clients also request CLI's location in case of not having them locally, using on-demand lookup calls to the coordination service. The cache clients communicates with cache data servers to access data using read, write clean, and write dirty operations. Of these, the write clean, dirty operations inform the data server as to whether the data being written into the cache is clean, in case of a cache insertion, or dirty, in case of a cache update. Finally, write back calls atomically write interdependent dirty data to the storage backend to ensure that the storage backend can perform consistent point-in-time snapshots for disaster recovery. We conducted a preliminary study using 363 block storage workloads from production systems. Details of these workloads are in the paper. We simulated cache network access corresponding to 40 gigabit network and storage access corresponding to AWS EVS with 2 milliseconds IO latency. We used the ARC cache replacement algorithm for comparing local cache performance and cache performance. Using ARC, we obtained the number of read hits. All writes in local cache are misses, while all writes in cache are hits, either insertions or updates. Finally, writes to the cache layer are fault tolerant, simulated using primary backup replication operations. We model a local cache system where an application accesses local SSD-based cache, incurring 5.3 microseconds for reads. It uses the write-through policy, so all writes are simulated misses. The cache miss latency is 2 milliseconds for accessing a block storage backend. With cache, reads incur 13.3 microseconds network round trips. Writes incur 4 network hops for accessing a leader and a single follower of the replication group servicing the write. In this first set of results, we compare the average read and write IO latency across the 363 production storage workloads. We find that there are improvements available in cache due to its larger capacity relative to the local cache. We vary the cache size of a local cache up to a maximum of 10% of the workload footprint and a remote cache up to 20%. Read latencies are similar when the size of the local cache and cache are the same, with cache latency reducing up to 6% when we increase the cache size in cache to 20%. In the case of writes, cache using the write back policy and primary backup replication scheme reduces latency by as much as 90% relative to the local cache, which must write all data to the high latency backend storage. In this next plot, we present the overall IO latency for the same workloads. We can see 31% reduction in average IO latency when local cache and cache are sized to 10% of the workload footprint, with additional improvements up to 36% when the cache size is increased to 20%. As future work, some of the challenges in cache include addressing the fault tolerance and consistency requirements for having a caching solution that supports caching rates. Also, selecting the class sizes in cache is the cache small unit of access represents a trade-off to optimize for both cache fragmentation and metadata overhead, at the coordination service side. In addition, the design of an allocation scheme, the corresponding eviction strategies, as well as the data placement and load balancing policies across different cache data servers are also important design decisions in cache. Finally, another goal in cache is the design of a distributed cache resource allocation algorithm that guarantees user-defined level of quality of service to the application. We would like to thank the National Science Foundation for funding the research, member of the Systems Research Laboratory, and other collaborators at Florida International University. Thank you.